Today is
Yes.
welcome to Dr. Aglesh Pandey from DRDO SSPL Delhi. I think we already introduced to earlier he gave a talk in the semiconductor technology. Today is important talk is advanced technology for future trends in the semiconductor processing. Let us welcome to Dr. Aglesh Pandey deliver his lectures.
Okay. Shall I start?
Yes, sir. Start, sir.
Okay. Good morning, everybody. Now I'm going to deliver a lecture on advanced technologies for future trend semiconductor processing. And this is the plan of the talk. First, I'll tell about the introduction, in which we'll tell about the semiconductors, which is essential for many cutting-edge technologies and devices. And then I will explain about the elemental semiconductor-based advanced technology, in which I will slightly touch about the silicon technology, that is the elemental silicon germanium. Then I will I will go for the 3-5 semiconductor technology, in which compound semiconductor using gallium arsenide, gallium nitride, and uh, indium phosphide based some technological advancement I will explain. Then I will go for the wide bandgap semiconductor, advanced semiconductor, in which I will explain about the silicon carbide wafer technology and wide gap semiconductor uh, silicon carbide as well as gallium nitride based devices and MICs. Then slightly I will touch about the silicon carbide based MEMS, in which slightly I will tell about the MEMS technology and aluminum nitride based sensors. Then at the last I'll explain about the future trend semiconductor device and device processing. So this is the plan of the my talk. Now, uh, now in the semiconductor, basically semiconductors are essential technology enables that the provide many of cutting edge digital devices. The global semiconductor industry, the global semiconductor industry is set to continue the robust growth well into the next decade due to emerging technologies. The emerging technologies basically are the artificial intelligence. Right now, there is a lot of boom in artificial intelligence. Then 5G, 6G. Right now, people are working in this area. The Internet of Things, coupled with a consistent spending on R&D. According to Moore's law, according to Moore's law, according to Moore's law, uh, the number of transistor on the circuit.
Sir, not getting wiser.
Now, according to Moore's law, the number of transistors on the integrated circuit has doubled roughly every 2 years.
Sir,
Feature size
echo is
decreases.
coming, sir. Sir, echo is coming. One will be mute, one will be used, sir.
Okay. Actually, one another device I have used.
Yes, sir. One device you can use PPT, and one device you can use mute. Like
You
that, you
can
can
mute
also.
me in other device.
Yes, sir. Divisor, you can mute one, sir.
Yeah, I have done, sir. You can carry on.
Okay. Now you can go ahead, sir. No problem.
Okay. According to Moore's law, the number of transistors of an integrated circuit has doubled every 2 years, as everybody knows, and feature size decreases and speed of the device increases. The constant technological development has facilitated the creation of seemingly endless stream new devices that have become the central of daily life in the 21st century. Now, the 21st century, several advanced semiconductors materials or you can say technology come into the picture. So right now, people or you can say industries are working in the advanced semiconductor materials and devices. Now, the importance of the semiconductor. Right now, you can see the global semiconductor, the average growth rate are 6%, compound annual growth rate of the global semiconductor revenues around 6%. And the semiconductor devices can be used in the various transportation, military, aerospace, data chem, telecom, medical, automatic, industrial, and various other consumer electronics. So the basically you can see the worldwide semiconductor revenues basically as the how the worldwide revenue is increasing starting from 1997 96. You can see the worldwide semiconductor revenues around 10%, but it is more than 60 or 70%. And similarly, you can see the percentage is uh, slightly fluctuating, but it is also increasing. The average August 20 it is around 4.9% per year. So now in the basically the evolution of the technology, basically three eras of demands in the from 1960 to 1980. It is a computer centric. Whatever the technologies have been developed, it is computer centric. But after that, more after the 90, it is mobile centric. Mobile centric is nothing but the data has to be centered into the mobile, but now it is a data centric. Whatever the data number of data we are generating, that is can be used, or whatever the technology has been developed, it is data centric. So in our daily life, data are very important, as well as business, or you can say daily life, or maybe innovations. So the digital era enabling the radical shape in the relationship between the technology capabilities and business opportunities. The explosion of new technologies, that autonomous vehicles, digital healthcare, quantum computing, cryptocurrency, mining, etc., are the driving the need of more industry-wide collaboration. And this industry-wide collaboration enables companies to compete the data-centric era. Now, in the advanced technologies, technology semiconductor, basically the elemental and compound semiconductor are showing the pivotal role in various technological, civil and defense applications. Various emerging novel materials in 3-5 like gallium nitride, indium gallium phosphide, or you can say other indium gallium aluminum nitride, and nano energetic material, assessing their environmental health and safety impacts along with the social responsibility implications, cater the various technologies. Many elemental semiconductors like silicon, germanium are widely used in various technological applications. Silicon everybody knows, but in germanium, basically germanium is a IR material, so IR windows are also used in the using the germanium bulk crystals. In the compound semiconductor technologies like 3,5 gallium arsenide, silicon carbide, gallium nitride, aluminum nitride materials are being used, and also various technological R&D work is going on in these materials. Various technological works, technological R&D work is going on. These semiconductor technologies can be enabled uh, widely using the various high frequency and high power device applications. Now, basically, high power and high frequency device are very much needed in our defense uh, defense point of view. Suppose our soldier is sitting on the tank, and there are various uh, you can say attacks are coming onto the soldiers, like unmanned aerial vehicles, fixed wind AC guided bombs, or satellite jammer, laser jammer, NBCs, top attack munitions, and soldiers are sitting on the tank. So if the high frequencies are coming onto the soldier, he can uh, he can receive the signals, and accordingly he can the soldier can take decision. So the high frequency devices are very much needed for our defense applications. So for high frequency devices, basically the wide gap materials can be used for such devices like gallium nitride and silicon carbide. But silicon carbide and gallium nitride can be also used for high power devices also. So for high frequency, not only the silicon carbide, gallium nitride, some gallium arsenide or indium phosphide devices can also be used. But for power devices, gallium nitride and silicon carbide and other wide band gap materials can be used. So for the defense point of view, this you can say our high frequency devices are very well utilized. Now, since we are talking about the high frequency devices, now you can see that this is the microwave chart starting from microwave frequency band have completely transformed how to communicate the harness technology. Now you can see that here it is not very much visible, but frequency from 50 hertz to some gigahertz you can see. Now in the gigahertz, basically, let me see first because it is very it is not visible. Uh, so starting from this from energy from frequency from 50 hertz to gigahertz up to terahertz, picohertz, like that. So satellite frequencies starting from LS can be divided in several frequency microwave frequency band, in which L band, S band, C band, X band, Ku band, K band, Ka band. These are the several frequency satellite frequency ranges, in which X band is starting from 8 gigahertz to 12 gigahertz, Ku band 12 to 18 gigahertz, K band 18 to 26 gigahertz, Ka band 26 to 40 gigahertz. Now, the microwave band and frequency band and application is its various application and advantages, uh, because if we go for the S band, S band can be use satellite communication. For C band, it is a long distance radio telecommunications, and for Ku band, it is satellite communication, DTH applications, and K band, it is a radar, satellites, astronomical observation, and autonomous vehicles. And for Ka band, people are working right now the Ka band also, that is satellite communication. It is very well used these type of devices right now. Now come to the elemental semiconductor. Basically, elemental semiconductor people are used basically the silicon or germanium. This is the one of the slide which I will tell about the bulk crystal growth technology to device fabrication technology to microchips. Here you can see the silicon uh, in bulk single crystal have been grown by the different techniques like Choklatsky or here Choklatsky or float zone method. And this bowl have been grown and it has been sliced to make a silicon wafer. So silicon wafer, for slicing the silicon wafer, there is another technology that is called the silicon uh, silicon wafer technology to fabricate the silicon wafer. This is also several steps have to be used for shaping, then orientation, determining the orientation using the X-ray goniometer, then cutting, then polishing, then chemomechanical polishing. So then AP ready wafer has to be grown. So such type of different steps has to be done to make it silicon wafers. So right now we are getting a silicon wafers with different, you can say, sources, and it is very cheap. But you know there are a lot of technological challenges are there, and after all the challenges we get the silicon wafers. Then if you want to take a silicon based devices, you want to make a silicon based devices, then what happened, we have to go for the silicon we have to go the processing. In the processing, basically the three main steps which I would like to tell you. One is lithography. Lithography is nothing but the pattern transfer onto the silicon wafer, which which require. So for that, one has to make a photo mask. And the photo mask has to be kept onto the above the silicon sapphire, and UV light exposure will be there after resist coating. Then pattern has to be transferred. After patterning, transfer the patterning. Patterning is a doping has to be done. Doping makes the substrate p-type or n-type, whatever we are needing, and doped wafer after doping, its passivation has to be done. In the passivation, it's basically the deposition has to be done. In the passivation, basically PVD or CVD technique have been used, and in on the sample where the uh, lithography have been done, one has to do the metal deposition also to make it ohmic. So for that, we one has to use the sputtering, or you can say evaporation technique. After that, it's etching. Sometimes metal etching has to be done. So artificial etching has to be done. So after metal etching, its device have been several devices have been fabricated onto the wafer. So it's a dicing, then packaging. These are the normal steps to make a device. And this microchip testing is also very important. After testing, this type of uh, packaged device have been used onto the systems. Now the different silicon based devices and their applications. Basically in the silicon based devices, either one has to take for the gate turn off thyristor, or you can say insulated gate bipolar transistors, or MOSFETs, or high voltage ICs, power ICs. These are the several devices used in which the silicon are very well used, and the operation frequencies are starting from 10 hertz to
இல்ல இல்ல
uh,
பண்ணுங்க.
what happened? Am I audible? Hangaval?
Audible.
Audible. Acha, okay. Some murmuring
Oh.
is coming, that then I
No,
thought that
it's
there was
fine,
some
fine, sir,
problem.
fine.
Fine. Okay. So what happened? These are the operating frequency. You can see starting from uh, 100 hertz to 1 megahertz, and various appliances in which like washing machine, home appliances, air conditioners, microwave, or you can say car switch, in which switch power supply has been used, robot, motor control, UPS, in which silicon based device are very well used. So this is the silicon based device, but still people are working the silicon based devices to make ICs and several advanced electronic uh, devices. So silicon, I don't think silicon can be replaced, but people are working in the silicon as well as some other wide band gap semiconductors uh, right now. Now come to the compound semiconductor. Basically, compound semiconductor, uh, either it is 3-5 semiconductor or some other compound semiconductor. The 3-5 semiconductor, basically there are several applications. Like it can be used in the microwave devices. It can be used the high electron mobility transistors. It can be used for photo detectors, UV visible IR terahertz. It can be used with the single photon source detectors. And in the solar cell, 3-5 semiconductor are widely used, because if you go for the space application based solar cells, in the space application based solar cell, it's indium gallium phosphide, aluminum indium phosphide, indium gallium arsenide, and germanium. These triple junction or multi junction solar cells are widely used to enhance the efficiency, because the if you take a three or more solar cell, and it can be attached randomly. So when the light falls, it can it will absorb the all the radiations uh, from UV to IR. So its external quantum efficiency as well as photoconvergency will enhance. So for and gallium arsenide, or if you have the 3-5 semiconductors, are radiation hardness also. So uh, in this field, solar cell, this gallium arsenide, or you can say compound semiconductor 3-5, are widely used. Now it can be used for LEDs by changing the composition of 3-5 materials. Various LEDs can be fabricated, and these can be used for the various optoelectronic devices. Now lasers, UV visible lasers, UV visible IR terahertz, it can be also be used. Now if you go for the lattice matching, or by changing the composition, lattice can be matched as well as lattice matches, and band gap can also be determined by changing the uh, compositions. So these are the common semiconductors like arsenide, gallium arsenide, aluminum arsenide, indium arsenide, or indium aluminum arsenide, quaternaries, aluminum antimonides, in which in gallium arsenide, indium antimonide can be used in the IR devices. IR technology is widely used. Gallium phosphide and indium phosphide or aluminum gallium phosphide can be used for the visible LEDs also, and some mixed quaternary can also be used. Nitrides, I'll take a nitrides. I can explain it later. Now, if we go for the 3,5 gallium arsenide based HEMT technology, in the gallium arsenide based HEMT technology, basically this is just a type of MOSFET in which indium gallium arsenide is a barrier layer where the and in the doping in this case the delta doping has to be done. So carriers, by applying the bias, the carriers have been come onto the well, and it is 2 DG can be 2 DG is formed in between channel and substrate layer. So the carriers are confined in this area. So the mobility is quite increased. And this HEMT, high electron mobility transistor, can be used in microwave and millimeter wave communication, imaging, radar, radio astronomy, and power switching. And it can be also utilized in the cell phones, power supply, adapters, direct broadcast satellites, receiver to radio astronomy, electronic warfare systems such as the radar systems. It can be used in the power switching, integrated circuits, high gain and low noise at high frequency greater than 600 gigahertz for power gain to frequency greater than 1 terahertz. So gallium arsenide, but right now gallium arsenide technology people have already used. It is not in the R&D section because the up to 2010 or 15 it has been saturated. So people have come onto the gallium nitride, or right now people have started to work on the in gallium oxide. So these type of hemp technologies are right now it is in the people are started working. Now come to the indium phosphide hemp. Indium phosphide hemp basically this is also the high electron mobility transistor, and 2 DG formed at this region, that is the indium gallium arsenide and indium aluminum arsenide in between these two layers. And here you can see that in this case a gate is nothing but is a T gate. So the gate length has been reduced to increase the frequency of the devices. So high electron mobility transistor offer the best performance for low noise and high frequency applications. It is extremely low noise amplifiers and excellent gain performance at microwave frequency. At cryogenic temperature, these properties improve further. At cryogenic temperature, these low noise and high frequency can be improved uh, um, more. And typical application in the field of deep space communication and radio astronomy, this indium phosphide based HEMTs can be used. Now come to the band gap semiconductor. Basically, in the wide band gap semiconductor, gallium nitride and silicon carbide. Gallium nitride, everybody knows its band gap is around 3.4 electron volt, and silicon carbide, its band gap is around 3.2 electron volt. Because several polytypes exist, and every other in the gallium nitride, polytypes band gap is also uh, uh, band gap is also changing. So as compared to the silicon, its band gap is slightly high, but another wide band gap semiconductor, that is diamond, its band gap is around 5.47 electron volt. So it's in the right here you can see that there are several uh, silicon 4S SiC gallium nitride and diamond, and its parameters comparison are shown here. And one can see that silicon carbide and gallium nitride, this is the hexagonal in which all the properties have been shown. Like silicon, its temperature compatibility is low as compared to gallium nitride and silicon carbide. Its band gap is also low. Its electron mobility is slightly high as compared to silicon carbide, but low as compared to the gallium nitride. Its electron saturation velocity is also low as compared to silicon carbide as well as gallium nitride. Thermal conductivity is low as compared to silicon carbide, but almost similar in terms of the gallium nitride and melting point also. So the wide band semiconductor in which silicon carbide and gallium nitride, one can see that if we go for the high power devices, silicon carbide is high power but its frequency is low. So silicon carbide is widely used or very well can be used in which uh, various electro vehicle charging, DC to DC converter, and as power devices application, power storage. But as far as high frequencies devices and slightly maybe power is low, in that case, gallium nitride can be widely used. So the wideband semiconductor is addressed the state-of-art electronics used in the chargers, adapters for consumers, appliances, electro electric vehicle charging, telecom, switch mode power supplies, solar and battery formation for industrial application, as well as onboard charging, high voltage to low voltage DC to DC converters for automotive applications. These are the several applications of the wide bandgap semiconductors. Now, come to the silicon carbide bulk technology. First, I will slightly explain about the bulk silicon carbide crystal growth by PVT and its wafer fabrication technology. Silicon carbide can be grown by the physical vapor transport method. In the physical vapor transport method, silicon carbide polycrystal has been kept onto the crucible, and then then it's heating then by heating it has been up to 2200 degrees centigrade. The silicon carbide transported and transported vapor has been transported, and it has been formed the silicon carbide bowl onto the seed crystal. So uh, so you can see that the temperature is around 2200 degrees, source to seed around 100 degrees centigrade. Difference is this. So this is the flow diagram showing the crystal growth of various fabrication and various fabrication process. After this is the silicon carbide PVT reactor furnace, and this is silicon carbide polycrystal, and this is silicon carbide bowl. After growing the silicon carbide, it has to be cut to make a silicon carbide wafer. So for that, there is a wire saw machine. In using that wire saw machine, the cutting has to be done. Cutting and slicing, cutting process, slice silicon carbide from the silicon carbide ingot. After cutting the silicon carbide, is shaping its means rounding and wafer surface grinder is also there like this one. Then chemomechanical polishing. This is the surface grinder. This is the chemomechanical polishing where the uh, sometimes it will call the chemical mechanical planarization also. So to make the samples with different slurries like silicon carbide slurries, diamond slurries, to make the silicon carbide is a in the epi ready wafers. But one more thing which I have not included here before that, because the as grown wafer is 4-degree cut, so it's a orientation will also be done. For orienting, there is X-ray goniometer. Using that part, it has to be oriented along a 001 direction, and there is a flat demarcation also be there, like it is a primary flat or secondary flat, and the primary flat grinding system machine will is also there to make it primary cut, primary flat, secondary flat grinding, then cylindrical grinding, then this type of several steps like cutting, wafer surface grinding, chemomechanical polishing, then characterization. And after characterization, this is the one of the wafer which can be used for the silicon carbide substrate, or this silicon carbide substrate can be used to make a silicon carbide based devices. Am I audible?
Audible,
Okay.
correct.
Everything is
Go
okay
ahead.
now?
Yes,
Actually,
sir.
I'm
Yes,
not
sir.
able
Voice,
to
everything is
see.
okay. Go
I'm
ahead.
not able to see
Yes, sir.
any
Your
of.
voice is clear.
Okay, thank you. Thank
Everything
you very much.
okay.
Thank you
Everything
very
okay,
much.
sir. Your voice is clear.
Okay, okay, okay. Now, just I'm one slide I've included here. There are something wrong because silicon carbide spelling is wrong here. Silicon carbide bulk growth and wafer characterization. In the bulk growth, as I told you, this is the one of the diagram which I have made. This is the bulk silicon carbide source material, and this is the graphite crucible, and this is the induction coil heating. And here it is a seed crystal, and above the seed crystal there is a crucible lid. Sometimes if the in the seed has to be uh, pasted onto the lid. If the pasting is not in the proper way, then again some defects will come. So the defects will come in the form of uh, micropipe densities, or sometimes uh, some other polytypes has to be grown. So this is the slide where I would like to tell you, because the growth window is around 2200 or 2300 for growing the 4H crystal. So growth window is very low, very narrow region, and the temperature is very high, around 2200 degrees centigrade. So any ambiguities into the furnace, or any temperature variation have been occur, which that is occurring unintentionally. So there is a finite possibility to become, while we are growing 4H silicon carbide, it will grow up 6H SiC or 15R silicon carbide. These are the polytypes. So the 4H, because the stacking fault energy between uh, 4H silicon carbide, 6H silicon carbides, and 15R silicon carbides are 0.6233, 0.4840, and 0.4440 kilocalorie per mole. So slight fluctuation, if occurring, then it will form another polytypes. So for 4H SiC crystal, the temperature window for keeping the polytype stability is very low. Any fluctuation in the temperature profile or pressure growth cavity may cause the unintentional supercooling and deviation of carbon to silicon to carbon ratio at the growth front, which further lead to formation of foreign polytypes. So uh, suppose in the foreign polytypes have been formed onto the crystal. So how to identify that it is a 4-HSIC or 6-HSIC and 15R silicon carbide? So this slide shows that structure and Raman characterization, which will tell about the formation of 4-HSIC or 6H silicon carbide. See, one of the wafers which we have taken and X-ray rocking curve measurement, which will tell about the crystalline quality of the wafer, have been done at several places. In the suppose, and it has been taken around 5 places. In one place, we got some splitting have been done. So in the at that place, we did the uh, SEM, uh, scanning electron microscopy, and in the scanning electron microscopy, it was found that there are two regions, a demarcation, two regions which shows might be 6H and 4H. So what we did, this is our results. In that we did cathodoluminescence. In the cathodoluminescence, luminescence, what happens, defect emission of 4H and silicon 6H are quite different. The reason being, there are some defect emission position are different. So uh, so we thought that in this uh, sample, or you can say wafer, there is 6N and 4H silicon carbide are present. So to confirm it, we did the X-ray diffraction, the theta to theta scan. In the X-ray diffraction gonio scan, theta to theta scan, it was found that there is a 004 and 008 peak are clearly showing. But apart from that, there are three intense peak, smaller intensity have been identified. So these are the peaks which is related to 005, 006, and 007, and these are equally spaced. So these peaks are kinematically should be kinematically absent, but it still we are getting. The reason being because silicon carbide is a periodic structure, 4H periodic structure. This is natural superlattice type of structure. So that is why these peaks are shown. But in another region, apart from we have identified 006 and 0012 planes. And apart from that, several small peaks have been identified. It was showing that in the silicon carbide 6H, there should be 1, 2, 3, 4, 5. 5 equispaced satellite peaks have identified. And 15R, there are 4 equispaced peaks have identified. So it is confirmed that in the 6H region, uh, apart from 6H, there are 15R polytypes also present. because the stacking fault energy between 6H and 4H is very less. So if temperature inhomogeneity will be there, or some pressure ratio or carbon to silicon to carbon ratios have been changed, so 6H have been formed, and 6H, because of the stacking fault energy is very less, so automatically 15R have been also formed. So further confirmation, we did the exotopography. In exotopography, basically it is the X-ray diffraction mapping. By choosing an appropriate plane in the grazing incident geometry, exotopography have been done. We have identified that this region is 4X SIC. And apart from this range region, there is a 16 HSIC and 15 RSI silicon carbide is also present. And several dark spots have been also identified. These dark spots is nothing but these are the micropipes present into the crystal. Now, we did the Raman spectroscopy. In the Raman spectroscopy, what happened? Apart from 6H, one range region have been taken from 102 to 250. So X-ray mapping have been done. X-ray spectroscopy have been taken at different points, and mapping have been performed at around 3.5 mm to 10 mm. 2 mm like. So we found that 6H, 15R and 4H, all the polytypes are present. And in some places there are some other colors are showing. These colors are nothing, but these are the micropipes, because whenever the uh, laser is focusing, and in the micropipe place, focusing is disturbed. So we are getting a high intensity at that place, high integrated intensity. So that is why it was assumed that this is it. We think that it is a micropipe, and micropipe it was confirmed by the exotopography also. So this is the normal structure and Raman characteristics from silicon carbide, and it is very important to identify the silicon carbide polytypes. Now, in the silicon carbide technology, the bulk growth technology, as I explained you, it is very important to uh, sublimation growth of the silicon carbide bulk crystal have been grown. Then silicon carbide bowl have been come out, and it's a wafer polishing. Uh, and then epitaxial growth have been done. So after that, silicon carbide device processing. In the processing, lithography, deposition, etching, metallization. This is the front end process. Then dies on the wafer. Then back end process, back grinding, dicing, flip chip, die shaping. Then back end labeling. Then after that, the device packaging. The device packaging basically either it is a discrete devices or the power module. Discrete devices have been various applications, and in the power module, power inverter, stack, and uh, it can be used in the high speed bullet trains also. Now, the silicon carbide power devices basically, if we take about the silicon carbide MOSFET structure, it is showing the uh, uh, difference between the comparison between the silicon carbide MOSFET structure and silicon carbide MOSFET structure, silicon MOSFET and silicon carbide MOSFET structure. Now, here one can see that the silicon carbide MOSFET structure, the large reduction in electrical resistance. If the electrical resistance decreases, so it's a power already will increase. So this type of devices or Schottky diodes can be used in the various silicon carbide based devices, which can be applicable in various applications like electro vehicle power, electro vehicle charger, in the solar area, industrial, it's an industrial application, or wind energy applications, high speed rails, power gridded, because high power devices needs high power grids. It can be used servers, smart appliances. So these are the common silicon carbide device applications where the silicon carbide are widely used, or maybe in the future it will be very well used. Now come to the gallium nitride based technologies. In gallium nitride, basically everybody knows the gallium nitride has an isotropic nature. It is a spontaneous as well as a piezoelectric polarization. Both will exist because of non-polar nature. It's a uh, non-polar nature. So this is the crystal structure of uh, gallium nitride. This is the nitrogen phase. This is the gallium phase. And along the 00C direction, it is a spontaneous uh, uh, ionicity, microscopic polarization, and lack of due to lack of symmetry, it's a spontaneous and macroscopic polarization.
Yeah, what was the
Yes, am I audible?
Yes, sir. Audible. I think somebody disturbed.
Acha, okay. Now, if we see that in the silicon carbide based high electron mobility transistor, uh, right now, very well used silicon carbide, gallium nitride based high electron mobility transistor. The basic device structure is shown here. Basically, there is a substrate. Substrate can be either silicon or silicon carbide or gallium nitride. There is a nucleation layer. Either it is aluminum nitride, gallium nitride, then gallium nitride buffer layer, and two-dimensional electron gas is formed between the barrier layer and buffer layer. Barrier is aluminum gallium nitride. Then device fabrication has to be done. There is a source, gate, drain, and whenever the uh, it is several steps which is shown here, but I'm not going to much detail. So high electron mobility transistor can be used in the various applications like data center servers, AC to DC converters, power PV inverters, photovoltaic inverters, and this and high frequency and high power based devices. Now these are two devices which is showing that is a vertical devices and lateral devices. These are the GaN on silicon, which is a power the future. Now, gallium nitride based HEM technology for high frequency application. There are two structures which I am showing here. One is a gallium algan GaN HEMT structure grown on silicon carbide substrate, and here the stack is shown here. Gallium nitride buffer layer and two-dimensional electron gas is formed between the. There is a special layer also between the aluminum nitride spacer and gallium nitride, and it is to increase the you can say mobility. And this is the X-ray diffracto X-ray rocking curve measurement. It's a simulation result of the gallium nitride based HEMT devices. Now you can see that using this uh, simulation, one can identify the composition of aluminum gallium nitride, its thickness, strain, all the parameters have been extracted. Then another structure, that is a indium aluminum nitride based barrier layer have been used. Apart from aluminum gallium arsenide, whose composition around 25%, here indium aluminum nitride based barrier have been used. So because indium aluminum nitride around 17%, it is very well lattice matched with respect to the gallium nitride. So there is a several advantage of indium aluminum nitride gallium nitride HEMT as compared to aluminum gallium nitride HEMT. Its X-ray diffractogram have been done to find out the composition, thickness, all those parameters. Its 2 dg concentration have been determined using the Hall effect to find out the it is 1e17, but indium aluminum nitride it is 2e17. So carrier concentration is slightly increased. So because of increasing the carrier concentration, its a 2 dg mobility is reduced, but sheet carrier concentration to 215 to 300. So surface morphology in both the cases, step surface morphology have been identified. The basic advantage is this, because this uh, indium aluminum nitride, because of low thickness of the barrier, it can be used for the high frequency devices. In Ku band, indium aluminum nitride on gallium nitride based HEMT can be used. For algan GaN X band, it can be like in lies on the X band frequency band. So as the thickness decreases, its the frequency increases, and the gate, because the gate length has to be reduced. Uh, if it is a 25 nanometer, the gate length is higher as compared to indium aluminum nitride. But if we go for the 17 nanometer, it means thickness is decreased. So in that case, we can go for the T gate or low thickness, low length gate. So its frequency increases. So it can go for the high frequency. If one can go for the, if we use apart from the InGaN GaN, if one can use the aluminum nitride, gallium nitride channel, aluminum nitride channel, then it can be used for the carbon also. So another high frequency, one has to decrease the thickness of the barrier layer so that the low channel gate length can be fabricated. Now this is showing the comparison between the appliance range, application range of silicon carbide, gallium nitride device for each power capacity and operating frequency. In the silicon carbide, as I told you, it can be used the IGBTs, electric vehicles, for low frequency refrigerator, washing machine, and for high frequency for silicon carbide MOSFETs or uh, or you can say other power conditioners. So this can be used home energy management systems using and solar power generation systems is usable in various weather conditions. So it is necessary to power conversion system can supply a stable power using a lithium ion battery using the silicon carbide. So one can develop the new charging system using silicon carbide devices in order to achieve high conversion efficiency. So wideband semi materials are able to improve the efficiency in power conversion applications compared with the legacy materials such as silicon carbide together with its 3 5 counterparts, gallium nitride offers the advantages in terms of energy that have made it to focus attention in the power electronics development. Now the various applications, one here you can see that it can be used the SMPS. Here gallium nitride as silicon carbide both can be used, but the silicon carbide either is a Schottky barrier diode or maybe a MOSFET. By HVDC's power supply, silicon carbide have been used large LED screen, large screen HD TV. In the diodes are silicon carbide, Schottky barrier diode, and gallium nitride HEMT can be used for inverters, UPS, and various industry equipments. Silicon carbide based Schottky barrier diode and MOSFET are used for home energy management system. Basically, silicon carbide, Schottky barrier diode, or MOSFET have been used for electric vehicle quick charger. Silicon carbide contactless power transistor. Silicon carbide have been used for USB power devices, gallium nitride as well as HEMT, uh, refrigerators, washing machine, air conditioners, LEDs, and lighting. Silicon carbide, Schottky barrier diode. For gallium nitride, HEMT. And similar solar power, wind power, silicon carbide, Schottky barrier diode, or MOSFET. These are the various applications of silicon carbide and gallium nitride based devices which people are started either using or will start will start in the future. Now come to the sensor technology. Sensor technology, basically I'll touch about the slightly silicon based MEMS or aluminum nitride based MEMS. This is the micro electromechanical silicon MEMS are the micro electromechanical system, is the integration of mechanical elements, sensors, actuators, and electronics on common silicon substrate through microfabrication technologies. These are the micro MEMS, micro pumps, micro uh, MEMS micro gear, MEMS micro mirror devices, and MEMS head sheet display. So these are the MEMS based devices. MEMS, these made of the components which is MEMS can be made with the components of 1 to 100 micrometer in size. Devices vary from below 1 micron to several mm. Functional element of MEMS are miniaturized structures, sensors, actuators, switches, and microelectronics. Microelectronics. Now MEMS components, basically in the MEMS component, what happened? Uh, there is a microelectronics. In the microelectronics, basically uh, Micro device is the brain that receives the process and makes the decision, and data comes from micro sensors. Micro sensors is constantly gather data from the environment, uh, pass data to the microelectronics for processing, can monitor mechanical, thermal, biological, chemical, optical, and magnetic readings. Micro actuator acts as a trigger to activate external device. Microelectronics will tell micro actuators to activate devices. Microstructures, extremely small structure built onto the surface of the chip, built right into the silicon of MEMS. Or the micro MEMS processing, basically first one has to design the sensor. Sensor designing is very important. There are several softwares available which design the MEMS based sensors. Then patterning. Transfer the pattern onto the material after deposition in order to prepare for etching. Patterning techniques include some type of, in the patterning, basically either photolithography or sometimes another lithography which is common. Then etching, there are two types of etching. Either it is wet chemical etching or dry etching. Wet chemical etching, which is dipping the substrate into the chemical solution that selectively removes the material process, provides a good selectivity. Etching rate of the target materials higher than the mask material. Then dry etching materials sputtered or dissolved from substrate with plasma or gas variation. Basically, in the dry etching, uh, in the wet chemical etching, sometimes it is a isotropic in nature, anisotropic nature. Like silicon, if you are etching silicon, and silicon is 100, one its orientation is 100, and like KOH etching will be there. So KOH etching will etch vertically, but if you are using silicon 111, then it etched slanted way. So in that case, if we use the vertical etching, and we are using a silicon 111, then in that case one has to go for the dry etching. So dry etching, as I explained you, the plasma has been formed. Choosing the method, desired shape, etch depth, uniformity, surface roughness, process compatibility, safety, cost, availability, environment effect, it can be chosen. So in that case, dry etching can be done. Now, in the silicon substrate, basically two types of micro machining can be done: bulk micro machining and surface micro machining. In bulk micro machine, what happen? The technique involves selective removal of the substrate to produce a mechanical component. Like silicon have to be etched. Uh, so in that case, chemical process or chemical used to etch out the material, that is called the bulk micro machining. But in the surface micro uh, machining, what happened? Either bulk in the bulk micro machine, either it will be isotropic or anisotropic. But in the case of surface micro machining, in the process, what happened? A sacrificial layer has to be deposited onto the substrate, and in the sacrificial layer, there is a pattern has to be have to be uh, uh, have to be cut out. Pattern has to be device layer constructed on the top, deposition the pattern, removal of the prairie layer, allow the movement of the structural layer. Then after that structure have been deposited, then it is removal of the sacrificial layer. Then this is the microstructure have been formed. This is called the surface micro machining. So this is one of the figure which will tell about the how the sacrificial layer, uh, how the structure have been fabricated onto the substrate, uh, this using the surface and bulk micro machine. Now in the MEMS process, there is a wafer bonding. In the wafer bonding method, that involves joining two or more wafers together to create a wafer stack. Three types of wafer bonding: direct bonding, anodic bonding, intermediate layer bonding. All require the substrate that are flat, smooth, and clean in order to be efficient and successful. And here one of the basically in the silicon, what happened, while DRI, their high aspect ratio fabrication should be there. Deep reactive ion etching enables very high aspect ratio etching to be performed on the silicon substrate. Side walls etching can also be done. depth of the etch can be hundreds or even 1,000 microns into the silicon substrate. This is the figure. You one can see that this is the mask and some etching process have been done, and after etching, deposition of the polymer have been deposited onto the top of it. Now this is the MEMS operation, basically sensors and actuator. Three types of the transducers are there. Either it is a capacitive, piezoelectric, or thermal. In the capacitive, what happened is the capacitance have to be varied in the MEMS operation. And the piezoelectric, due to piezoelectric nature of the material, while applying the field, it's you can say due to high D33, it's a variation in the while applying the mechanical. It's acrylic, while applying the while taking the external, uh, you can say uh, uh, environmental sensing can be done by uh, changing the shape of the material. So these are the MEMS operation on, and thermal temperature is changing. And here you can say this is the resonators, and this is the, here you can say by changing the environmental, or you can say changes, now it is changing. So basic benefits of the MEMS operation is a much smaller area, cheaper and alternative. In the medical market, it can be used, can be integrated with the electronic system. Its speed, lower thermal time constant, rapid response time, power consumptions, low actuation energy, low heating power. Now, the application of the MEMS, it is usually in the form of pressure sensor. Medical, it is widely used.
Divakar, you can mute the people.
What happened?
Hello?
What happened?
No, somebody is disturbing.
Okay. So in the application, basically the MEMS can be used in the various medical application like pacemaker applications. Is a pressure sensor can be used, implanted coronary pressure measurements, intraocular pressure monitors, and endoscope pressure sensor, infusion pump sensor. It can be used in the glucose monitoring, insulin delivery, MEMS tweezers and surgical tools can be used. Cell, antibody, DNA, RNA measurements devices, temperature sensors, IR sensor, navigation sensor. In the car, various sensors have been, MEMS-based sensor have been people used, are right now using various sensors in which gyroscope sensor, navigation sensors, or various sensors are used. I am not going to much details of these sensors. Airflow sensors, and air conditioning compressor sensors, fuel pressure sensors. MEMS-based sensors are widely used in the car also. Now, sensor using the aluminum nitride, because previously I told about the gallium nitride and or indium gallium nitride. Now, come to the aluminum nitride, because of piezoelectric coefficient is around 11 to 12, 10 to 11, but it is very stable material. Its thermal conductivity is very high, its electrical resistivity is very high, it is chemically stable. So, and its acoustic velocity is very high. It can also be used in the MEMS-based devices. Some of the work which I did, I would like to explain. Someone of students worked in this area. Basic application is the MEMS, microelectronics and medical sciences. Energy harvester. It can be used in the energy harvester also. SAW-based devices, due to high caustic velocity and high piezoelectric coefficient, can be used in the high devices, in the SAW devices also. Surface acoustic wave-based devices. Deep UV diode, UV detector used as a passivation layer and use the buffer layer in HEMT. These are the common application of the aluminum nitride-based material. Now, in one of the aluminum nitride thin films, the residual stress have been determined using the X-ray diffraction, and its MEMS oscillometer have been designed. In the MEMS oscillometer, basically in the device, piezoelectric oscillometer structure consists of thick proof mass around 800 micron to 800 micron and 300 micron, suspended by 4 beams. It is showing here. A dimension of each beam is 400 micron into 200 micron into 10 micron. An aluminum nitride layer of 0.85 microvan is integrated on top of the suspended oscillometer structure, and behavior of the structure is simulated using the Coventor software. And The effect of the residual stress generated during the deposition of aluminum nitride layer is seen on the model frequencies and static response of accelerometer structure. Here you can see that this is the aluminum nitride structure, and this is the silicon structure, and these are the 4 beams, and dimension is shown here. Now, 3 model pattern of the accelerometer structure. Basically, in the one case, when aluminum nitride there is no stress. Another case, aluminum nitride is residual stress minus 600 megapascal. One can see that the model frequencies uh, uh, are altered while applying the residual stress. And in the case of deflection, one can see that in that case deflection is changes. So deflection is zero at residual deflection at zero stress. Deflection is minus 600 megapascal stress, and one misses stress also changes. So one can see that here one can see that deflection at 0 megapascal proves mass displacement by changing the gravitation g 50 g, it is changing linearly. But in the case of applying in the residual stress present in the film, it is non-linear behavior, and the proof mass deflection is also shift. There is an offset present into the sample. So normalized stress sensitivity is found to be alter 1.33 10 to the power minus 3 per g at noise residual stress to 1.26 minus 10 to the power 4 at minus 3. So while designing, one has to know the proper residual stress of the sample, so that using the fabricator, whatever the results one is expected, that can be that one can get. Now, another structure is the mushroom shaped aluminum nitride based piezoelectric resonator using the aluminum nitride membrane. Since I am presenting it into the PDF file, so this video I can't show. But in this case, what happened? This is the silicon carbide post, and this is the aluminum nitride mushroom, like a mushroom. So top of aluminum nitride disc on of the mushroom shaped structure has the diameter around 500 micrometer, which is supported by the cylindrical post diameter 250 micron and height is around 400 micron of bulk micro machined silicon material. Mushroom shaped resonator structure will be helpful for generating different acoustic frequencies by easily varying the mode shapes of piezoelectric aluminum nitride disc attached on the silicon paste post. So impact of residual stress. Basically, in the sample, 3 samples have been taken whose residual stress have been changed. So aluminum nitride disc initially, you can see the piezoelectric disc different residual stress, no stress is there. Then in that case, the residual now shape is changing. Mushroom sides showing some stress, its frequency is changing. But in this case, it is changes is large, but while the residual stress is very high, it is showing a large changes. So this is the mode shape of the aluminum nitride resonator structure. Aluminum nitride thickness around 700 nanometer, 0 megapascal. Aluminum nitride thickness 700 nanometer minus 1050 megapascal. And similarly, as the thickness increases, the residual stress stages, and its frequency, or you can say resonant frequency is changing. This is the model frequency response of the mushroom shaped piezoelectric resonators. While changing the resonant frequency, it's without stress, and with the stress it is changing. So, and the Q factor is also changing. So now the aluminum nitride can be used for energy harvesting also. Uh, Here you can say by the vibration in is the signal output changed. Signal output is changing, and in here the aluminum nitride piezoelectric layer has been present here. By applying some voltage, initially there are not any changes. Wind is while applying the wind, initially there is no change, but as the wind speed increases, you can see the voltage increases. So the aluminum nitride can be used for the energy harvesting also. Here one can see this is the aluminum nitride beam have been shown here. The array of the are connected in series and parallel, and the maximum generated powers are 0.935 and 3.315 microwatt under 1G respectively. Then a full wave rectifier can be used to convert alternate current into the direct current. The output power loss of the array series and parallel connection is reduced. So aluminum nitride can be used for the energy, although the efficiency might be slightly low as compared to other piezoelectric materials. So slightly I'll show about the 2D semiconductor technology can also be used in the is advanced technology. People are using these 2D materials also to the various sensing, or you can say modulators use people are using, like memory, CPU memory, sensors, and future vision devices. These are the widely used right now. Now semiconductor technology trend in the future, trends futuristic. In that, what happened in 2023, there is a uh, one paper I have gone, one article we have which we have seen, that semiconductor technology trend in a futuristic manner. The futuristic, what happened, there are 10 things are into the uh, have been explained. And basically the things are internet of the things, another is artificial intelligence, then advanced materials, novel architecture, uh, novel architecture with advanced packaging, uh, then 5G technology, in-house chip design, fabrication technologies, automatic chips, sustainable manufacturing. And in these 10 semiconductor technologies, there are several startups emerging, companies companies are working. 1336 companies have been working in this technology for futuristic trends. And now internet of the things devices, I'm just reading all the things, you can go through this one. Internet of the things press certain demands such as a smaller size, diverse connectivity technologies, and lower power consumption. To address these requirements, semiconductor manufacturers focus on sensors and integrated circuit development. Artificial intelligence, it is a rapid rise of AI solution right now, is forcing the chip industry to develop AI ready hardware. Semiconductor companies also integrate AI into the manufacturing workflows to optimize the operation and improve the product quality. Advanced materials, as I explained you, because of Moore's law, as the structure size decreases, speed increases. So silicon carbide, gallium nitride, which is the advanced materials, and which can be used in advanced material. Novel architecture, due to fierce competition and faster processing speeds, the chip industries leveraging novel architecture. Startups build non-volatile memory chips, integrated heterogeneous 3D enabled designs, and use the nanotechnology to develop the novel processor architectures. Advanced packaging, electronic packaging technologies significantly affect the chip power, performance, cost. Advanced packaging solution allow manufacturer to merge multiple components into the single electronic devices with better signal connections. It includes the techniques such as the multi-chip modules, 3D ICs, 2.5D ICs, fan out packaging, and system in packaging, among the others. 5G, as you know, the 3G, 4G, and 5G. In-house chip design, chip semiconductor companies are translating the in-house chip design for better control over the product roadmaps and supply chains. Fabrication technologies, the continuous maintenance of the chip geometry requires the precise and detailed orientation fabrication technologies, and brings to overcome all the challenges and complexity. Automatic chips, there are automotive chip. Modern vehicles with autonomous driving capabilities have already altered demand patterns for automotive semiconductors. These vehicles require better electronic solutions for improve the connectivity, in sensor, battery performance. Sustainable manufacturing, to maintain the increasing interest of semiconductors, simultaneously meet the ecological requirements. Manufacturer scrutinizing emission among the entire supply chain. Chip fabrication generate massive amount of emission. So the come to the major associated challenges in advanced semiconductor device processing. First, suitability of the device with proper application. Whatever the device one has to be used, that is suitable for the proper application. Another is a suitable for high frequency and high power.
Sir, what happened, sir?
Just suitable and high quality wafer substrate, and dimensional should be controlled. Device processing should also be controlled. There are several residual steps will be there that has to be accounted while fabricating the devices. Film substrate compatibility should also be should also be there. Organic and organic residue, parasitic capsules leakage, proper packaging and testing. These are the major associated challenges advanced semiconductor device processing that has to be accounted while fabricating advanced devices. Now, I would like to acknowledge, this is the end of my talk. I would like to acknowledge Director SSPL who has given permission to present some of the work. Member of Characterization Division, Dr. Shankar Datta, Dr. Mahadev Bhatt, organizer of the Faculty Development Program, ISM, IIT Dhanbad. Now, thank you.
Sir, thank you, sir. The excellent talk for novel semiconductor recent trend and manufacturing technology. Sir given is more overview and as well as how the gallium nitride device is working in various field in the optoelectronic devices and solar cell and all the things. Now talk is open for discussion. Any few questions from faculty members and students, and clarification also. Sir given more excellent talk regarding gallium nitride things, and as well as future trend, how the semiconductor technology is working, the various field. Hello?
Yeah, I'm here.
No, sir, you are available. I am asking your faculty members,
If
audience.
if there is no question, you can ask them to. If there is any
Yes,
question,
sir.
you can write in the chat box also.
Yes, you can write chat box also if you have any questions. Then we can. I can read. I think everybody is hungry. Now only 5:30. 2 o'clock start. I started the journey. Now I think now
No problem,
5:30.
no problem.
Maybe.
Sir, such a nice presentation, sir.
Okay, thank you.
Maybe a few questions, 1 or 2 questions.
Yeah, can I have?
Yes.
Sir, actually, these GAN devices, are
Yes.
they, I mean, are we using these devices for commercial applications?
Commercial, yeah, definitely. It is using in the commercial applications also. Since I am from DRDO, so we are looking for the defense applications, but people are using for the commercial applications also.
So, which kind of commercial applications?
Like as I explained you, high power devices like electric vehicles, and in fact LED lasers also. These are the some various applications I can
Okay.
tell you.
So in general, they are not being used currently. They are not being used currently in kind of domestic applications like
Right now
maybe in washing
people are
machines,
not
maybe in
using that.
shops.
Yeah, because it is very costly now, but it can be used. It can be used. It is
Okay,
actually
okay.
the thing is gallium nitride or silicon carbide based devices very costly. So in compared to silicon,
Yes.
uh, it is the cost is more than 10 times, I think so. So it is very difficult.
Yes. So they
It
are
can be
compound devices,
used.
huh? Yes, these are compound semiconductors.
Yeah, it is a compound semiconductor.
Yeah. They are costly. Okay. Thank you, sir.
Okay. Anything else?
Anything? Any questions? Any other question or clarifications? If you have anything, then you can contact the SAR also in DRDO,
Sure.
SSPL New Delhi available. You can directly contact me or directly contact the SAR also. Sir is the semiconductor device, the lab head. He can, if you interested, you can write a DRDO project with him also. If any faculty members are,
Actually, one thing,
that
since,
also,
since
that is the information.
Sangaval told me that I tell you, there is a separate portal in DRDO website. There is a ER-IPR portal. In the ER-IPR portal,
Yeah.
you can go through that portal and you see what are the, how to write the projects to the to DRDO, and in which field DRDO is working. You just try to find out where you can contribute for the country, for the DRDO as well as country. In that area, you should write a project, and you will get, because enormous money is there. But the thing is, the project should be related to our defense applications.
Sir, can we organize a session for my students, sir?
In DRDO,
No, sir. In our college, sir, Greater Noida.
Greater Noida.
Yes, sir. Actually, I am
In which college you?
IMT group of colleges, sir.
Okay, there, it is very near. That can be done. You can take my
Okay, sir.
mail ID to Thangaval, and
So,
that can be done. It is not problem.
sure, sir, sure.
I think further no more question. Let us thank Dr. Aglesh Pandey. He's given an excellent, nice presentation and a more advanced semiconductor manufacturing technology. Let us big thank to. I think one more question is asking, sir. So, DRDO importing any semiconductor chip?
DRDO importing semiconductor chips.
Yes, sir.
Yes,
Chat box.
actually, what happened? Semiconductor chips, wherever it is needed, and DRDO can't be fabricated, that can be imported. But if the DRDO can fabricate that chip, we are not importing that one. Okay.
Already the DRDO is very famous for the gallium nitride device, and HEM2 structure is the fabricated and they made
actually,
up to the product levels.
That I explained in my talk also.
Yeah, yes, sir. That is the things. I hope there is no more question. Let us thank to Dr. Aglesh Pandey for an excellent, nice presentations, and welcome, sir.
Thank you, Thangabal.
Yes, sir. Thank you, sir. Thank you very much.